Hello and welcome. In this video, we will explore the topic of related rates, a key application of differentiation in the IB mathematics analysis and approaches higher-level curriculum. By the end of this lesson, you will be able to identify variables and constants in a problem, establish a relationship between them, differentiate that relationship with respect to time, and solve for an unknown rate. Related rates problems involve finding the rate at which one quantity is changing by relating it to other quantities whose rates of change are known. The core idea is to use the chain rule to differentiate an equation with respect to time. Consider a classic example: a ladder sliding down a wall. The ladder has a fixed length. As the foot of the ladder slides away from the wall, its horizontal distance, which we'll call x, increases. At the same time, the top of the ladder slides down, so its vertical height, y, decreases. The rates of change for x and y are related. The rate of change of x with respect to time is written as dx/dt, and the rate of change of y with respect to time is dy/dt. These are our related rates. The method for solving these problems is a systematic 5-step process. First, draw a large, clear diagram. Second, write down all the given information, clearly distinguishing between variables that change over time and constants that do not. Third, find an equation that connects the variables. This often involves geometry, like the Pythagorean theorem or trigonometry. Fourth, differentiate this equation with respect to time, t. And finally, substitute the values for the specific instant in time you're interested in and solve for the unknown rate. Let's apply this method to our ladder example. This is a standard problem you should be comfortable with. A 5-meter-long ladder rests against a vertical wall. Its feet slip, and at the instant when they are 3 meters from the wall, they are moving at 10 meters per second. We need to find the speed at which the other end of the ladder is moving at this instant. Step 1. Draw a diagram. We have a right-angled triangle formed by the wall, the ground, and the ladder. Let's label the horizontal distance from the wall to the foot of the ladder as x, and the vertical height on the wall as y. The length of the ladder is a constant 5 meters. Step 2. Identify variables and constants. The variables are x and y, as they change over time. The constant is the ladder's length, 5 meters. We are given that at a specific instant, x equals 3 meters, and the rate of change of x dx dt is 10 meters per second. We are asked to find the rate of change of y dy dt at this same instant. Step 3. Find an equation. Since we have a right-angled triangle, we can use the Pythagorean theorem. The equation is x squared plus y squared equals 5 squared, which simplifies to x squared plus y squared equals 25. This equation relates our variables x and y. Step 4. Differentiate with respect to time. T. This is the crucial step where we use the chain rule. Differentiating x squared gives 2x times dx d. Differentiating y squared gives 2y times dy/d. And the derivative of the constant 25 is 0. Notice how we differentiate each term with respect to its own variable, then multiply by the rate of change of that variable with respect to t. Step 5. Substitute and solve. We need to find y at the instant when x equals 3. Using our original equation, 3 squared plus y squared equals 25, which means y squared is 16, so y is 4 meters. We take the positive root as it's a physical distance. Now we substitute all known values into our differentiated equation. We have 2 times 3 times 10 plus 2 times 4 times dy/dt equals 0. This simplifies to 60 plus 8 times dt equals 0. Solving for dt, we get negative 60 over 8, which is negative 7.5 meters per second. The negative sign is important. It indicates that the height y is decreasing, which makes sense as the ladder is sliding down. The question asks for the speed, which is the magnitude of the velocity. Therefore, the other end of the ladder is moving down the wall at a speed of 7.5 meters per second. We have successfully used the 5-step method to solve this related rates problem. A common mistake in these problems is to substitute the specific values too early. Let's see why this is incorrect. If we then differentiate this equation, The derivative of 25 is 0, and the derivative of 25 is also 0. We end up with 0 equals 0, which is not helpful. We've lost the relationship between the rates of change. Always differentiate the general equation first, and only substitute the specific values at the very end. Now let's tackle a problem that involves trigonometry. This is a common type of related rates question in the IB exam. Consider a right-angled triangle ABC with the right angle at A. The side AB has a fixed length of 20 centimeters. The angle ABC, which we'll call theta, is increasing at a constant rate of 1 degree per minute. We need to find the rate at which the side BC, which we'll call x, is changing at the instant when theta is 30 degrees. Step 1. Diagram. We have a right-angled triangle. We label the angle theta at B, the side AB as 20, and the hypotenuse BC as x. Step 2. Variables and constants. The constant is AB equals 20. The variables are theta and x. We are given that d theta dt is 1 degree per minute. A crucial point for differentiation is that angles must be in radians, so we convert 1 degree to pi over 180 radians per minute. We are asked to find dx dt when theta is 30 degrees, which is pi over 6 radians. Step 3. Equation. We need an equation relating theta and x. Since we have the adjacent side and the hypotenuse, we use the cosine function. Cosine of theta equals adjacent over hypotenuse. So cos theta equals 20,000 x. It's often easier to differentiate if we write this as x equal to 20 times cos theta to the power of -1. Step 4. Differentiate with respect to toj t. We'll use the chain rule on the right side. The derivative of x with respect to t is dk dt. On the right, we differentiate the outer function, which is the power rule, giving -20 times coawisic theta to the power of -2. Then we multiply by the derivative of the inner function, cos theta, which is -sin theta. Finally, we multiply by d theta slash d. This simplifies to dx dt equals 20 times sin theta over cos squared theta, all times d theta dt. Step 5. Substitute and solve. We substitute our values for theta and d theta sar d. Dx dt equals 20 times sin pi 6 over cos squared pi 6 times pi over 180. We know sin pi 6 is 1/2 and cos pi 6 is root 3 over 2. Squaring cos pi 6 gives 3/4. Plugging these in, we get 20 times 1/2 over 3/4 times pi over 180. This simplifies to 20 times 2/3 times pi over 180, which is 40 pi over 540, or 2 pi over 27 centimeters per minute. This is approximately 0.233 centimeters per minute. So, the side BC is increasing at a rate of approximately 0.233 centimeters per minute. This example highlights the importance of using radians for angles in differentiation. Let's look at a problem involving volume. This often requires finding a relationship between the dimensions of a 3D shape. Air is pumped into a spherical weather balloon at a constant rate of 6 pi cubic meters per minute. We need to find the rate of change of the balloon's radius at the instant when the radius is 2 meters. Step 1. Diagram. A sphere. We label the radius as r and the volume as v. Step 2. Variables and constants. The variables are v and r. We are given that the rate of change of volume, dv dt, is 6 pi cubic meters per minute. We need to find the rate of change of the radius, dar dt, when the radius r is 2 meters. Step 3. Equation. We need the formula for the volume of a sphere. The volume 5 is equal to 43p r cubed. This equation connects our variables v and r. Step 4. Differentiate with respect to toj t. We'll use the chain rule on the right side. The derivative of v with respect to t is dv dt. On the right, we differentiate 43 pi er cubed with respect to r, which gives 4 pi r squared, and then multiply by d r dt. This is the chain rule in action. Step 5. Substitute and solve. We substitute the given values into our differentiated equation. We have 6 pi equals 4 pi times 2 squared times dr slash dt. This simplifies to 6 pi equals 16 pi times dr slash d. To solve for dr plus h dt, we divide both sides by 16 pc, which gives 6 pi over 16 pc or 3/8. So, at the instant when the radius is 2 meters, the radius is increasing at a rate of 3/8 meters per minute. This problem demonstrates how to handle volume formulas in related rates. Let's try a more complex problem involving a conical tank. This will require us to find a relationship between the radius and height of the water. Water exits a conical tank at a constant rate of 0.2 cubic meters per minute. The tank has a total height of 8 meters and a top radius of 6 meters. We need to find the rate at which the surface radius of the water is changing at the instant when the water is 5 meters deep. Step 1. Diagram an inverted cone. We draw the tank and the water inside it. Let h be the height of the tank, r be its radius. Let h be the height of the water, and r be the radius of the water's surface. Step 2. Variables and constants. The constants are the tank's dimensions, h is 8 and r 6. The variables are the water's volume, v, height h, and radius r. We are given that dv dt is negative 0.2 cubic meters per minute. It's negative because the water is exiting, so the volume is decreasing. We need to find dr/t when the water height h is 5 meters. Step 3, equation. The volume of a cone is v equal 1/3 pi r squared h. However, this equation has two variables, r and h. We need to eliminate one of them. We can use similar triangles. The triangle formed by the water and the triangle formed by the tank are similar. Therefore, the ratio of their radii to their heights is the same. R over h equals r over h. Plugging in the tank's dimensions, we get r over h equals 6 over 8, which simplifies to 3/4. Since we want to find d/t, it's easier to express h in terms of r. From our similar triangles, h equals 4/3r. Now we substitute this into the volume formula. Step 4. Differentiate with respect to t. Differentiating v equals 4/9. P r cubed gives dv dt equals 4/3 pi r squared times d/dt. This is our differentiated equation. Step 5. Substitute and solve. We need the value of r when h is 5. Using our similar triangles relationship, r equals 3/4. So when h is 5, gr is 3/4 times 5, which is 15/4 meters. Now we substitute dv dt and r into our differentiated equation. Negative 0.2 equals 4/3 pi times 15/4 squared times dt. This simplifies to negative 0.2 equals set 5 pi over 4 times dar dt. Solving for dar dt, we get negative 0.8 over 75 pi, which is approximately negative 0.034 meters per minute. The negative sign confirms that the radius is decreasing, which is expected as the water level falls. This problem shows how to handle situations with multiple variables by using geometric relationships to simplify the equation. Let's conclude with a classic optimization problem that uses related rates principles, the shadow problem. A ground-level floodlight is 40 meters from the foot of a building. A 2-meter tall person walks directly from the floodlight towards the building at 1 meter per second. We need to find how fast the person's shadow on the building is shortening at the instant when the person is 10 meters from the building. Step 1. Diagram. This is a similar triangles problem. Let L be the floodlight, B be the building, P be the person, and S be the top of the shadow on the building. Let X be the distance from the person to the building, and L be the height of the shadow. The total distance from the light to the building is 40 meters. Step 2. Variables and constants. The person's height, 2 masanasis, and the distance to the building, 40 satias, are constants. The variables are x and y. We are given that the person is walking towards the building, so their distance x is decreasing. Therefore, dx dt is negative 1 meter per second. We need to find di dt when x is 10 meters. Step 3. Equation. We use similar triangles. The small triangle formed by the person and the light is similar to the large triangle formed by the building and the light. The ratio of height to base is the same. So 2 over 40 minus x equals y over 40. This gives us our equation, y equals 80 over 40 minus x. Step 4. Differentiate with respect to t. We can use the quotient rule or rewrite the equation. Let's rewrite it as y equals 80 times 40 minus x to the power of negative 1. Now differentiating with the chain rule, dt equals negative 80 times 40 minus x to the power of negative 2 times the derivative of the inner function, which is negative dx or dt. This simplifies to dt equals 80 over 40 minus x squared times dx dt. Step 5. Substitute and solve. We substitute the given values. ddt equals 80 over 40 minus 10 squared times negative 1. This is 80 over 30 squared times negative 1, which is negative 80 over 900. This simplifies to negative 2 over 22.5, or approximately negative 0.89 meters per second. The negative sign indicates that the shadow's height is decreasing, or shortening. So, the shadow is shortening at a rate of approximately 0.089 meters per second. This problem is a great example of how similar triangles are used to set up the initial equation. Let's recap what we've learned. We've seen that related rates problems are solved using a 5-step method. First, draw a diagram. Second, identify variables and constants. Third, find an equation connecting the variables. Fourth, differentiate that equation with respect to time using the chain rule. And fifth, substitute the specific values and solve. Remember the key warning. Always differentiate the general equation first, before substituting any specific values. You are now able to identify variables and constants, establish relationships, differentiate with respect to time, and solve for unknown rates. These skills are fundamental for success in the IBAA-HL curriculum. To solidify your understanding, here are 5 practice questions in the style of the IB exam. Pause the video, try to solve them on your own, and then resume to see the fully worked solutions. Question 1. A square's side length is increasing at 2 centimeters per second. At what rate is its area increasing when the side length is 6 centimeters? Question 2. A 13-meter ladder leans against a wall. The foot of the ladder is pulled away from the wall at 0.5 meters per second. How fast is the top of the ladder sliding down the wall when the foot is 5 meters from the wall? Question 3. A circular ripple expands in a lake. Its radius increases at a constant rate of 1 meter per second. Find the rate at which the area of the ripple is increasing after 4 seconds. Question 4. A right-angled triangle has a fixed hypotenuse of 10 centimeters. One leg is increasing at 0.1 centimeters per second. At what rate is the angle opposite this leg increasing when the triangle is isosceles? Question 5. A conical pile of sand is being formed. The height of the pile is always equal to its radius. If sand is added at a rate of 10 cubic meters per minute, how fast is the height of the pile increasing when the height is 2 meters? Let's go through the solutions. First, question 1. The area of a square is A equals x squared. Differentiating with respect to t gives dA dt equals 2x times dx or dt. We are given dx dt is 2, and we want to find dA dt when x is 6. Substituting these values, we get dA dt equals 2 times 6 times 2, which is 24. So the area is increasing at 24 square centimeters per second. Next, question 2. Using the Pythagorean theorem, x squared plus y squared equals 13 squared. Differentiating gives 2x dx dt plus 2y dx dt equals 0. We are given dx dt is 0.5 and x is 5. First, we find y. 5 squared plus y squared equals 169, so y is 12. Substituting, we get 2 times 5 times 0.5 plus 2 times 12 times di dt equals 0. This simplifies to 5 plus to 4 did equals 0, so did is negative 5 over 24 meters per second. The top of the ladder is sliding down at 524 meters per second. Now for question 3. The area of a circle is A equals pi r squared. Differentiating gives d equals 2 pi r times d. We are given dara spot d is 1. We need to find r after 4 seconds. Since the radius increases at 1 meter per second, after 4 seconds, the radius is 4 meters. Substituting, dt equals 2p times 4 times 1, which is 8 pi. The area is increasing at 8 pi square meters per second. Question 4. Let the hypotenuse be c to 10, the increasing leg be x, and the angle opposite it be theta. Then sin theta equals x over 10. Differentiating gives cos theta, d theta d equals 110 d dx de. When the triangle is isosceles, x equals y, so x squared plus x squared equals 100, meaning x is 5 root 2. At this point, sin theta is root 2 over 2, so theta is pi over 4, and cos theta is also root 2 over 2. Substituting root 2 over 2 times d theta slash dt equals 110 times 0.1. Solving for d theta slash d gives 1 over 50 root 2 or root 2 over 100 radians per second. And finally, question 5. The volume of a cone is V equals 1/3 pi r squared h. We are given that r equals h, so V equals 1/3 pi h cubed. Differentiating gives dVt dt equals pi h squared times dh slash dt. We are given dVt is 10, and we want to find d when h is 2. Substituting, 10 equals pi times 2 squared times d. This simplifies to 10 equals 4p dht, so d is 10 over 4 pi, or 5 over 2 pi meters per minute. I hope these examples and practice questions have helped you master the topic of related rates. Keep practicing, and you'll find these problems become much more manageable. Thank you for watching.